All right, so we're going to wrap up section 4-1 in one last video. Hopefully this one will be just pretty short. We have one more example here to go ahead and find all of the absolute extrema for. So like we've been doing so far, we want to start out finding the derivative. The derivative of e to the negative x is negative e to the negative x. And the derivative of e to the negative 2x is going to be negative 2e to the negative 2x. And so we've got some simplifying of algebra to do here. We end up with this becoming a positive. So we have, and I'm actually going to reorder this so that we have positive 2e to the negative 2x minus e to the negative x. Okay. And I'm going to go ahead and actually factor this. I'm going to pull out an e to the negative x from both terms. And from here, that leaves us with a 2 and an e to the negative x minus 1 equals 0. Well, setting this equal to 0, e to the negative x never equals 0. So we won't get any values from this one. But this one we can set equal to 0. 2e to the negative x minus 1 equal to 0. Adding 1, dividing by 2, we get e to the negative x is equal to 1/2. And then we can use natural logs to solve for x. So if I take the natural log of both sides, I have negative x, and then ln of e is just 1, is equal to ln of 1/2. So x is equal to the ln, or negative ln of 1/2, or ln of 2. Either one, same thing. So we've found where this critical point occurs. Let's check whether it is positive or negative in different places here. So this is h prime, and again, just going back to that previous video, being picky here, this should have been g prime. And this is negative ln of 1/2, or you could write ln of 2, either way. And plugging in something less, let's say 0, something greater, let's say 1. You can calculate what this decimal is to help you figure out what to plug in. And if I plug in 0 to my not to the original function, to my derivative, I end up with something positive and something negative here. So that means that this is a maximum. And I need to also check my endpoints. So the points that I'm checking are h of 0, h of negative ln of 1/2, and h of 1. And plugging those values in, plugging in 0, we got 0. Plugging in negative natural log of 1/2, we get 1/4 exactly. Plugging in 1, we get approximately 0.233. Well, 1/4 is greater than 0.233, so this gives me my max, and this gives me my min. So my absolute max is equal to 1/4 at x equals negative ln of 1/2, or you could write positive natural log of 2. My absolute min is 0 at x equals 0. So that's it for those examples. This last example here, number 5, we want to prove that the function f of x has neither a local maximum nor a local minimum. So we want to do that by trying to find those. And if we can't find them, then that means there are none. So let's first find the derivative of this function. F prime of x is equal to 101 x to the 100th power plus 51 x to the 50th power plus 1. Now this looks like kind of a strange function, but this actually follows a quadratic pattern. The degree of this term is half of the degree of this term, and then we have a constant. So this follows a quadratic pattern. It's also a polynomial, and it's defined everywhere, which means it's a continuous function everywhere. So I'm going to set this derivative equal to 0. And because it follows a quadratic pattern, we can use the quadratic formula. But this might be a slightly different way of using the quadratic formula than you've done before. Rather than saying x is equal to, and then plugging everything into the quadratic formula, we'll say x to the 50th power is equal to, and then we can use the quadratic formula. So in this case, my b value is 51, so negative b would be negative 51, plus or minus the square root of 51 squared minus 4 times a times c, all over 2a. All right, now it's just a matter of simplifying all of that. So x to the 50th power. When I do negative 51 plus this radical divided by 2 times 101, I end up with negative 0.021. And when I do negative 51 minus all of this, negative 0.484. So we have those two values. Now that's x to the 50th. And when we take the 50th root of both of these terms, can we take an even root of a negative number? No, that would give us an imaginary number. These are not real. Okay, so what this means then is that there are no critical values. Well, if there are no critical values, then that means there's no local maxes and mins. And if there are no local maxes and mins, and we're not given an interval we're looking at, then we have no local maximum and no local minimum. So, therefore, we have proved what it's asked us to prove. Therefore, there are no local maxes or mins. And that brings us to the end of section 1, and hopefully that was clear.